Hey, Global Impact, it's Mr. Ellinger. This lesson is on ratios, rates, and conversions. Our learning targets for the lesson are to find ratios and rates, and we also want to be able to convert units and rates. Essential understanding for the lesson: ratios and unit rates can be used to compare quantities. Units and rates can be converted to solve problems. Background for the lesson: because ratios are not always written as fractions, you can choose to not call the numbers numerators and denominators. To prevent confusion, you may refer to them instead as the first term and the second term of the ratio. Okay, so ratio. What is a ratio? Well, a ratio could be a fraction, like 3/4. This same ratio could be written 3:4. That's the ratio of 3 to 4. We can write it in words, 3 to 4. Okay, so a ratio is just a comparison of two quantities. Now, I didn't put any units or any meaning to these numbers, but these are the three ways that we can write a ratio. Okay, a rate would be like, say you do 6 math problems in 10 minutes. So you do 6 problems per 10 minutes. A rate tells you how many or how often something occurs compared to something else. That's what a rate is. A lot of times rates involve time. Okay. A unit rate takes this concept of a rate. The condition here is that instead of saying we do 6 problems in 10 minutes, we would want to know how many problems do you do in 1 minute. The most common unit rate is miles per hour. All right, if you're driving on the highway, you might be going 65 miles per hour. Okay, 65 miles for every 1 hour. That's the unit rate, unit meaning 1. Let's look at some examples here. Suppose you're shopping for t-shirts. Which store offers the best deal? Store A has $25 for 2 shirts. Store B has $45 for 4 shirts. Store C, $30 for 3 shirts. Well, we could write each price that we are given as a ratio. Here we have $25 per 2 shirts. Here we have $45 per 4 shirts. Here we have $30 per 3 shirts. Write the ratio as a unit rate to compare. See, the information that we're given, it's a little bit helpful. Maybe in our head we could figure it out a little bit. But if we convert each one of these down to the cost per shirt, which is a unit rate, then we can answer the question. So 25/2 reduces down to $12.50 per 1 shirt for store A. Store B, it's $11.25 for 1 shirt. Store C, $10 for 1 shirt. And once we convert these unit rates, it's very easy to determine which store has the best sale, and that would be store C. Follow-up question here. If store B lowers its price to $42 for 4 shirts, does the solution to the first problem change? Well, let's take a look at that. 42/4, that's this information here. What's the unit rate? Well, 42 divided by 4 is 10.5. So $10.50 per 1 shirt. Still not a better deal than it is at store C. Store C, it's $10 per shirt. All right, to convert from one unit to another, such as feet to inches, we multiply the original unit by a conversion factor that produces the desired unit. A conversion factor is a ratio of 2 equivalent measures in different units. A conversion factor is always equal to 1, such as 1 foot over 12 inches. There's a table on page 814 in your text that you can see some common equivalent units of measure. It's in one of the appendices in the back of your book. We've got a problem here. A building is 1,450 feet tall. How many meters tall is the building? We're going to use the fact that 1 meter is approximately 3.28 feet. Right there, they give us the conversion factor. 1 meter per 3.28 feet. We have a building that is 1,450 feet tall. okay? And we want to know how many meters is that. So how should we set this problem up? It's going to involve one of two things. We're either going to divide 1,450 feet by 3.28, or we're going to multiply 1,450 feet by 3.28. The question is, which one? Well, I wrote 1,450 feet here. We're going to multiply this by the conversion factor. And the conversion factor is 1 meter over 3.28 feet. Okay. Now, after we multiply that, whatever value we get, the units are going to be meters, correct? This gives us a clue here. We're going to basically write 1,450 feet as a fraction. And that number is either going to be in the numerator of a fraction or the denominator of a fraction. What we want to do is we want to look at unit canceling, okay? And what I mean by that is, if I put 1,450 feet over 1, when I multiply here, see how I have feet in the numerator here and I have feet in the denominator here? Those feet units, if you will, cancel each other out. If one's in the numerator and one's in the denominator, when I multiply here, I'm going to get some canceling of units, and that's what we want to have happen here. So I know that gives me the clue that I need to know that 1,450 is going to be divided by 3.28 to tell me that this building is approximately 442.1 meters tall. We can also convert rates. For example, you can convert a speed in miles per hour to feet per second. Because rates compare measures in two different units, you must multiply by 2 conversion factors to change both of the units. So here's an example. An athlete ran a sprint of 100 feet in 3.1 seconds. At what speed was the athlete running in miles per hour? Round to the nearest miles per hour. So the question you have to ask yourself is, what has to be converted? And also, does it matter what conversion factor you use first? The problem that we know, the rate that we're given in the problem is 100 feet per 3.1 seconds. Now we're going to multiply, and I'm going to use the x for multiplication here, just this once. I'm going to multiply this by 2 conversion factors. So there's one, and here's the other. Our answer is over here. The units are going to be miles per hour. So what we need is we have to have miles on top and hours on the bottom of our fraction here, okay? Now what has to be converted is we have to convert feet to miles, and we have to convert seconds to hours. How many feet are in a mile? Well, 1 mile equals 5,280 feet. 1 hour equals 3,600 seconds. Those are our 2 conversion factors. So in this first spot here, I can use my miles and feet conversion, or I could use my hours and seconds conversion. It doesn't matter, because once we get everything set up, we're going to multiply everything together. All right, but look at our answer. We need miles in the numerator of our answer. So I'm going to go ahead and use the miles and the feet conversion factor here. And I have to make sure that I put 1 mile in the numerator and 5,280 feet in the denominator. My second conversion, if I pay attention to my answer, I know I need hours in the denominator. So I'm going to put 1 hour in the denominator. And I'm going to put 3,600 seconds in the numerator. And that's okay. I can have the 1 in the numerator and the other number in the denominator. This is saying 1 mile per 5,280 feet, and that's true. If I were to flip that fraction over, I would be saying 5,280 feet per 1 mile. Those are both correct because they're both equal or equivalent. But the key, again, goes back to my answer. I need to have miles in the numerator, and I need to have hours in the denominator. And if you remember the last example, I have a feet in the numerator in this rate, and I also have feet in the denominator of this rate. Those will cancel. I have a seconds in the denominator here, and I have a seconds in the numerator here. Those will cancel as well. So now I'm ready to multiply across. I've got my units, 100 times 3600, 360,000. 3.1 times 5,280 is 16,368. So I have these values, but the problem says round to the nearest mile per hour. This is not a unit rate. The answer is asking me for a unit rate because it wants the answer in miles per hour. I need to take 360,000 and divide it by 16,368, and I get to the nearest mile per hour, I get 22 miles per hour. So at what speed was the athlete running? Remember, we want to answer our question. The athlete was running 22 miles per hour. Have a great day, folks.